In the late 1980s, NASA set its sights on the ultimate prize in planetary exploration, a mission to orbit Jupiter. They built Galileo. At 2.5 tons, costing nearly $1.4 billion, it was a massive, complex piece of engineering. In October 1989, Galileo rode into orbit aboard the Space Shuttle Atlantis, beginning its long journey to the outer solar system. This was the agency's crown jewel. Decades of planning, the careers of hundreds of scientists, and the expectation of returning the richest scientific haul in history rode on this single spacecraft. A year and a half into the flight, with the probe safely away from the heat of the sun, engineers sent the command to open the spacecraft's primary communication tool. It didn't open. The 16-foot, umbrella-like high-gain antenna was physically stuck, held shut by just 3 jammed ribs. The original plan was for that main antenna to stream data back to Earth at over 134,000 bits per second. Now, they were forced to rely on a backup low-gain antenna, trickling data back at a tiny fraction of that speed. Without a fast connection, sending heavy, detailed image files of Jupiter was out of the question. The most expensive probe ever launched was effectively deaf and blind. You can't exactly send a mechanic hundreds of millions of miles into deep space to unstick an antenna. If the physical hardware couldn't be fixed, the engineers realized they had to fix the software. They decided to rewrite Galileo's primitive onboard computers while the spacecraft was in flight. Their strategy was data compression. If the pipe was too small for the files, they had to mathematically shrink the files to fit the pipe. They wrote 2 algorithms. The Integer Cosine Transform found similar pixel blocks in images and stripped redundant data. The second, LZW compression, built a dynamic dictionary for text telemetry, replacing repeating strings of data with a single short symbol. If this sounds familiar, it's because it's the exact same logic used today by Internet of Things devices, like remote smart sensors, compressing data right at the edge of a network to save battery life and bandwidth. NASA essentially turned a 1980s spacecraft into the solar system's first ultra-efficient smart device to bypass the physical limits of its broken hardware. They carefully beamed this complex new operating system across the solar system, flashing it into Galileo's severely limited memory banks. By December 1995, Galileo reached the Jovian system. It was time to see if the patch actually worked. Upon arrival, Galileo immediately dropped a descent probe straight into Jupiter's crushing atmosphere. The probe plummeted through the clouds, measuring temperatures and atmospheric pressure. But every piece of that groundbreaking data was completely useless unless the new compression software could successfully squeeze it back to Earth. The hack worked beautifully. Over the coming months and years, unprecedented data began to slowly but reliably paint across screens at the Jet Propulsion Laboratory. The discoveries poured in. On its way to Jupiter, Galileo had photographed the asteroid Eta, and the compressed images revealed a tiny speck alongside it, Dactyl, the first moon ever discovered orbiting an asteroid. As it toured the Jovian moons, the spacecraft captured intense, towering volcanic eruptions on Io. It was a direct look at the kind of colossal lava flows that shaped our own planet billions of years ago. Then there was Europa. The images revealed a surface covered in deep reddish scars and a complex web of fractured ice. Combined with magnetic data, these icy cracks provided evidence of a vast ocean hidden beneath Europa's frozen crust. The defining images of the outer solar system, the ones that still guide our search for extraterrestrial life, were not transmitted perfectly. They were heavily compressed, squeezed down to their mathematical essentials, and meticulously reconstructed back on Earth. Galileo's results filled planetary science textbooks with once speculative discoveries: active volcanoes on moons, asteroid satellites, and hidden oceans. Its physical hardware was incredibly fragile, derailed by just 3 stuck ribs on a single antenna. But the engineers who built it were remarkably adaptable. The mission proved that human persistence can overcome the failure of physical tools, even from across the solar system. Galileo proved that even in the silent, unforgiving vacuum of deep space, hardware constraints can be conquered by human code.